Question number 40. Question number 40 says the action of blotting paper on ink is due to what? The action of blotting paper on ink is due to what? So option A says diffusion. Diffusion is the movement of molecule from a region of high concentration to a less concentrated area. So molecules move from where it is concentrated and moves to a region where it is less concentration. So diffusion is out of the option. It's not. Osmosis is the movement of fluids, liquids from water molecules from a region of lower concentration to the region of higher concentration, with the intention of what? Balancing up the levels of concentration. So osmosis flows from less concentrated area to a higher concentrated area. So that is not what we want to use here. Capillarity is the movement of liquids through a very small space, maybe a very tight tube and all of those things, and that is essentially what we have here. The blotting paper on ink is due to capillary actions. So you see, blotting paper is used to soak up ink. Even is used as cosmetics these days for makeups, and maybe when you're wet and all of those things, to soak up the skins. When the skin is wet, they use blotting paper there, and the action is simply a capillary action because the fluid is made to pass through a very tiny area. Are you getting it? So here we are not talking about whether it's moving from a low concentrated area to a higher concentrated area, or from a higher concentrated area to a lower concentrated area. But what we want to use here is that it's made to pass through a tiny space of the paper. You understand? So that's why we have a blotting paper, and the action there is what? Capillary action. You understand? So the option here, your answer here is what? Capillarity. So the answer here is capillarity. So your diffusion is simply the movement of molecules, gas molecules most of the times, from the region of higher concentration to a less concentrated area, while osmosis is a bit of reverse, is the movement of molecules from a less concentrated area to a higher concentrated area. So your capillarity is the passage of fluid through a tiny space. So you have by your surface tension to be is the elastic, that's properties, elastic nature of liquid surface that makes it to what? Occupy the least area possible. The least area possible area. And that's why you see insects are able to stay on water. Insects that are a bit less, they are denser when they are supposed to sink into the water, but they are very dense, denser in insects. No, I'm not talking about the tiny insects this time. The dense insects, they float on water when they're supposed to sink. This is because of the water is behaving as a solid, you know, so you have that they are able to float on top of the water. So here, what we want to use here is the action of bloating water, the action of what? Bloating water is due to capillarity, please. Is a capillary action, is due to capillarity. All right, so that's your question number 40. Now moving on to question number 41, which says, when two mirrors are placed at an angle of 90 degrees to each other, how many images will be formed when an object is placed in front of the mirror? When two mirrors are placed at an angle of 90 degrees to each other, how many images will be formed when an object is placed in front of the mirror? So here, the number of image n is equals to 360 degree divided by theta minus what? 1. 360 degree divided by theta minus 1. Here we are giving theta to be equals to what? 90 degrees. So the number of image would now be equals to 360 divided by 90 minus 1. 360 divided by 90 is what? 4. So you have your n to be equals to 4 minus 1. So the number of image formed will be what? 3 images. 3 images. That's number 41. Now, moving on to question number 42 now. Says, if silicon is doped with phosphorus, what type of semiconductor material will be formed? So this is concept of doping, you know. What is doping? Doping is, you know, intentional introduction of impurities into intrinsic elements. You have an element, so intentionally you introduce an impurity into it with a sole aim of improving its structural electrical properties. Are you getting it? For instance, now, you know, semiconductors don't conduct electricity as much, you understand? So you want to improve its conductivity such that it behaves more like a conductor. So you would just do what we call an introduction of another element into that element such that it behaves more like a metal. Are you getting it? When they are not, you understand? So this concept is what we call doping. So instead of just helping that element do more, you understand? So like that. Now in this case, now we're talking about silicon. Don't forget your silicon has an atomic number 14. Okay, so now here, because we are talking about, okay, let me first of all tell us about doping. Doping is the intentional introduction of impurities. Is the intentional introduction of impurities, all right, into an intrinsic semiconductor for the purpose of modulating its electrical optical and what, or structural structural properties. Now here we are talking about silicon. Now for silicon, you know, we've seen this question somewhere where they were asking us, I think earlier, they're asking us which of the following is a semiconductors. We told ourselves then that silicon is the semiconductor, is a metalloid, is a trivalent metalloid, and a semiconductor as well. So you have for silicon, the atomic number is what? Its atomic number is 14. Now, so if we have to write its valency, so you have 2, 8, 4. Okay, so it has 2, 8, 4. Now, you know, it requires 4 to get balanced. Are you getting it? But he doesn't want to be actually get balanced. He just wants to flow. You understand? So he wants to behave like a metal. All right. So now, silicon can be doped with either a pentavalent or trivalent elements. What I mean is an element that has a valency of 5 or a valency of 3. You understand? So such, you can have phosphorus, for instance. You can have arsenic, for instance. You can have a boron, for instance. You can have an aluminum, for instance. So most important element that is usually used in you know, doping silicon is boron and phosphorus. You understand? But you clearly have other ones like indium, you know, and stuff like that. But all these are either having a valency of 3 or a valency of 5. So how does it work? So if phosphorus, for instance, now phosphorus, its atomic number is 15. So we have this to be 2, 8, 5. 2, 8, 5. Okay. Now, when a phosphorus becomes a dopant, so we're using a phosphorus to dope our silicon. You know, silicon actually requires 4 to get balance. Okay, so phosphorus gives it all its 5. Okay, so when he gives it all the 5, it means it's now oversaturated. He's having all its valency complete, then with an exception of one element that is now able to roll. So this element rolls like an electric charge, are you understand? And this moves around charges, are you getting it? And makes it behave more like he has a free atom, more like a melter would do, and which makes it conduct. You understand? For instance, now if you look at metals like sodium and all of those things, you know, their valence is maybe 1, 2, and all of those things that is actually allowed to roam around like charges. So this is what happens here. So when this one is having a valency of 5, okay, right? So this is having a valency of 5 valency. Okay, so now this happens when a phosphorus is doped with when a silicon is doped with phosphorus, you understand? So you have a free atom that is able to roam around and carry electric charges, are you getting it? And makes it conduct more. All right, so here you are going to have what we call an N doping. So when a silicon is doped with a 5 valent atoms like phosphorus or arsenic, here you have something like phosphorus or arsenic, you know, and a free atom is available that roams around and what carry charges. Are you getting it? This is called an N doping. So you have that to be equal to N-type doping. That's called an N doping. So N-type, that's what you have. Then that's first point to note. Let me go back there. So you note that critically. Know that. So note this as well. So when a silicon is doped with a trivalent atom like boron, like aluminium, like indium, then a hole instead of this one, you know, while it was doped with 5 valence element, you have a free element that is able to roam around. Here is a 3, and this guy requires 4. For goodness sake, for you to be stable. Are you getting that? You have only 3 to give. So when you give 3, then you know you're having 3 plus 4 that is got originally. It became 7. So one hole is created. Are you getting it? So one hole is created. So you have a dope. When is dope with that? So you have an hole is created which works directly the opposite of 5 valent doping. Okay, this is called a p-type. This is called a p doping. So you have that to be, so you can have that to be p-type doping. Okay, so I've just given you more than you require now. So let's look at that question again. If a silicon is doped with a phosphorus, what type of semiconductor material will be produced? So you have an N-type. So N-type semiconductor. That's what you got. So here N-type semiconductors is produced when a silicon is doped with a phosphorus.